So a couple of major challenges that we have with automated or fully populated circuit boards over, for example, solder paste, which we've been doing for many, many years, is tall components, reflective surfaces, odd shapes, and then the inspection speeds. So specifically tall components, or actually before I get into tall components, I want to talk a little bit about how 3D sensing is done that kind of allows you to understand what the goal is, how we accomplish it, and what the challenges are related to that. So in almost all 3D inspection sensors in our market today, there's some sort of triangulation going on, meaning that you have a source and a receiver that are at different angles. And the fact that they're at different angles allows the sensing technology to determine how high things are. And that's basically how everything works from a 3D sensing technology point of view in our industry. There's other ways of going about that, but they're really not practical for the speeds that are necessary for electronic assembly. So this is pretty much the standard way. There's different ways of doing this as well. There's laser stripes that you can set down. There's also moire or some sort of fringe pattern that's put down. But basically, at the root of it all is that you're trying to determine height by triangulating two different sources in the receiver. So you can see in this picture right here, you have a lighting source, it's going down at an angle, and then the detector's at a different angle. So that's the crux of it. And then what happens is that there's a deviation in the receive optics from the source optics if there's height. And what we do then is we measure the deviation of that fringe pattern, for instance, and that directly correlates to how tall this particular object is. And in this picture right here, we have solder paste. And this has been going on for years, doing this sort of thing. We do light stripes. This moire technology is reference to three-phase profilometry. And profilometry is a little bit different than like a laser stripe or a fringe like this, in that it's a sine wave, and the sine wave you get information at every point instead of, if this were just purely a stripe, you'd only get information at the transition points, so the edges. But the sine waves allow you to get, sorry about that. The sine wave allows you to get information at all pixels in the image. And so that is a very standard and common way of getting height information in our industry of the automated inspection. Advantages of this, it's widely used. It's been used for 15 years now in SPI. It's very accurate. You can get very accurate measurements. The disadvantage and why we haven't had 3D systems, 3D AOI systems 15 years ago is that the fixed fringe pattern really limits how much range you can do. Solder paste is very well confined to not very tall heights. When you have populated components, boards with populated components, the component heights are quite tall, and we need a different technology or an improvement over this technology in order to succeed in 3D AOI systems. So yeah, basically it's the height, and this is why it's a problem for AOI systems over SPI. So here's an example of a tall component, and then there's a very small component next to it. And the fact that we're doing triangulation sensing, we have to have an angle in here somewhere. And for example, if this component were 30 millimeters tall, there is going to be a shadow. So for AOI in components, real components, there is a shadow effect. It actually has to shadow because there's a triangulation going on there. So that's one of the major problems for AOI systems. The other thing that's a challenge for inspection vendors is the fact that AOI solder leads are very reflective, and you get into a situation like this where it's almost like a house of mirrors. All those solder joints are just like little mirrors, and they're reflecting all over the place. And when you get down into near board, very microscopic level, lights bouncing every which direction. And so here's kind of an example of what
what's going on there. So you've got light going down here, and it's supposed to bounce up in a triangulated sense, and you sense that. But what really happens is light goes down, it bounces from one to the other, and then that pollutes the result there. So you get bad looking results or inaccurate results because of reflections from one component to the next, and or solder joints from side to side. There's a lot more reflective surfaces in a fully populated circuit board than there are in solder paste, for instance. Solder paste is a very diffuse surface. It, relatively speaking, is very easy to image. So that's another one. Another challenge is odd shapes. This is an image of a board, and this is in two different domains. This is the 2D domain, which is a standard 2D image that you've seen, a video type image. And this is what we call a height map or a height image. And what this is brighter pixels represent taller heights. So it's a way of representing the 3D image of the board or the 3D information of the board by using an image to represent the height. The issue here is that not everything is nice boxes, step changes. You look at these leads right here, and you can see them going from tall to low in a very gradual sense. So understanding the transition here, and if that transition is important, then that's something that's difficult from an algorithm standpoint to address and identify. Also, I don't know how good this is going to turn up for you, but on the tips of the leads down here on this particular example, these were like arc welded or spot welded to this pad, and there's a divot in each of those. And to measure that divot is another thing it's not necessarily characterizable based on equations, but it's an attribute of this particular lead that's important, and inspecting for that is something that needs to be done as well. And so, and having it in the 3D domain, gives you a whole layer of additional complexity in that it's a different type of information. And then inspection speeds is another challenge. A lot of 2D AOI systems can struggle keeping up with line speeds of today, depending on what your line speed is and how many inspection tasks are there. But the fact that there's more inspection just inherently makes it more difficult to provide and keep up to the inspection speeds that are expected. So just to kind of go through some of the magnitudes of this, and that it's probably 10 times more images in order to do a 3D system than it is a 2D system. So a 2D system typically would have 2 to 3 images of different illumination types depending on your setup and capability. The 3D system, however, would require the same 2D images that you got previously, because a lot of inspection still is 2D inspection and requires it to be 2D inspection. So you have to do your 2D inspection as well. But the 3D inspection information acquires at least 6 images and likely more. And because we talked about that shadow effect, you have multiple projectors as well. So each of the 6+ images times 4 adds up. Plus, if you're using a monochrome detector, you need to take RGB images in order to get your color rendition of the 2D images. So this page is talking about there's just way more data in the 3D system than there is in a 2D system. With way more data, there's way more processing as well. So you've got all your existing 2D algorithms that you're doing and the various inspection tasks, plus all the 3D height information processing. You don't just get the images, you have to process them and turn them into the height maps that I showed earlier, plus the additional 3D tasks, the different lead measurements that you're doing, coplanarity results, any sort of volumetric measurements on solder joints and things like that. So the bottom line is there's way more images and there's way more processing in a 3D system than a 2D system, and the challenge is to maintain the line speeds that you need in order to keep the plants efficient and the productivity up. So what I want to talk to you today is about an architecture that addresses some of these issues, and the point of this whole talk is to educate you on understanding the sensing technologies of the AOI system that you get as you're looking into them, so that you can best determine how to get a system that meets the needs that you have. So this is an architecture that I'd like to describe a little bit. One thing that's different about this than most is that most SPI systems, in fact, almost all SPI systems, I don't know of any, that they have a projector that's off to the side and then one camera on the top. And depending on your architecture, you have multiple projectors around the sides, and you project those and you require those on one single camera. This particular architecture turns that around in that you're projecting here, but you're sensing on the side, so that there's 4 parallel 3D sensors on this particular architecture. And the other aspect of this is it's a flexible fringe projector. SPI would project certain fringe frequencies, certain patterns, and there wouldn't be a lot of programmability in that. Adding a programmable fringe projector enables a lot of flexibility. And then using different modeling techniques to address and inspect the odd components that I described earlier. Okay. So 3D sensing, multiple sensing, or single sensing. In a single system sensor, so this is that picture from before, you've got this illumination coming from one side, and because there's a shadow here, you lose information in this area. The only way to address that is to take images from the other side and fill in that gap of information. Now, granted, you have a gap here, but you got that in the previous angle. So you go around on the different angles, and really you need at least 4 to cover get all the information that you need, especially around tall components. And so that's what has to be happening in a single sensing system where the camera's up on top. You have the multiple projectors. By turning it around and projecting from the top, you can project once, and then with your parallel sensors, you can read them all at the same time. So you're acquiring your parallel information simultaneously. And the advantage of that is it increases our potential speed. And so if you look through here, each time you stop and you acquire images, you're taking them all in parallel. Whereas if you have a single sensor, you have to take each illumination serially, and in order to get the same number of images and the same quality of inspection, inherently, if it's a 4 projector sensor, or 4 projector sensor, it's going to be 4 times faster, or you're going to have to take 4 times more images in serial instead of parallel. And that allows you to acquire images of the panel faster. The flexible fringe projector is somewhat related to that in that you're getting multiple fringe frequencies. So the way that we address how to get the tall components is multifold. One is the multiple sensing. The other is you need different fringe frequencies. That first slide that I showed you that talked about how we had the fringe pattern and the deviation of the fringe pattern is the height. That works up until you run into the next fringe, and then it's ambiguous. You don't know whether or not that data is from, has been deviated because of height, or if it's actually down to 0 and it's a straight line again. So you have to present it with multiple fringe frequencies. So this is 3 different patterns that we're projecting onto the board of different frequencies. This one's a little harder to see on this projector, but there's a pattern up here going across like this at a very high frequency. This is at a lower frequency, and this is at a very low frequency. And the ability to project at these different frequencies allows you to have a much larger wrap range, we call it our inspection range in the Z domain, that can allow you to measure things up to like 24 millimeters tall or beyond even, based on the fact that you have these multiple fringe frequencies and you can combine those in a way that allows you to determine how tall things are. Another thing that you can do is change the direction of that. Because it's a fully programmable projector, you can change it so that instead of going in this direction, you're going in the opposite direction. The reason for that, I'll get into shortly, but allowing the ability to program your fringe projector to do anything enables you to get much better flexibility in your results. Okay, the reflections that I talked about earlier, having the ability to do the programmable fringe enables us to determine where reflections are and where reflections aren't. This kind of gets a little bit technical, but this is that cartoon, that I showed earlier, where there's multiple reflections. It's ambiguous whether or not things are reflecting or not, and that ambiguity gives you a false reading. So for example, right here, you have light coming down here, it can bounce across here and come back up here, or you can have light from over here bouncing down and coming back up here. Now, as I said earlier, this was a sine wave, so the difference in addition between these two interference patterns puts some error in there. What we do is we use different fringe frequencies in that same effect, and you can determine and separate what the real response is from the reflected response, in that you can get, because the behavior of the reflections different based on the frequency, you can determine, as you get multiple frequencies, you can determine what's real and what's not. And we use that to suppress the reflections such that when they come down, we recognize which one's the multiple reflection, which one's not, and that allows us to get better height images, more accurate and representative of what's truly on the panel. So there's a clean looking height image. So then modeling technologies. This isn't necessarily a 3D attribute, but it's related to using 3D information to do modeling. So there's a concept called principal component analysis. In a lot of inspection algorithms, you're using thresholding, where you find out a certain value and you threshold the minimum and the maximum, and you use that to determine pass or fail. What PCA does, or principal component analysis, it learns what normal is, and it does a statistical model of what normal is, and it uses that to detect abnormal. And this technology is used a lot in facial recognition. And so I've got a very handsome man up here, and this is an original image. This particular image is difficult to tell, but it's actually 5% larger than the previous image. And you can use tolerancing software to determine that 5%, but this could be a pass here. This could be, this is an accurate representation of what this man looks like, and the fact that it's 5% bigger overall proportionally is something that's acceptable. Whereas in this particular one, and maybe not so easy for you in the back, but in this one, his one eye, his right eye here on the left side, is 5% larger, but the rest of it is the original image. And it looks a little wrong, and that's kind of what principal component analysis can do. You could tolerance that eye at 5%, and it would pass in, if this was a pass, a 5% bigger eye would be fine. But in this particular case, that's not right. So, it's not just the tolerance on each individual attribute, it's the relationships between each other that's important, and that's what principal component analysis is. And so this is kind of a graphical representation of principal component analysis, in that you have real things like resistors that are little different sizes, different shapes. And just as an example, this is a graph of each of these with, or a set of these with length and width plotted. And there's a certain acceptable range of length and width. So you got your width variation, your length variation. And what principal component analysis does is it calculates that relationship, and it does the inspection based on the distance from the ideal. So something that is, way over here on the edge on length and deviant on width, that's far from the mean and would be a big distance, which would lower your probability. And that's a way of determining pass from fail. Again, it's It's using many different attributes, kind of combining them all together and learning what normal is so that it can detect the abnormal, and the abnormal being not necessarily something you'd be able to program ahead of time. It automatically learns that. And so in looking at the 3D information, so we've been using this for a number of years on 2D images. However, as I said earlier, this is a 3D representation of the same board. It's also as an image. So using principal component analysis to understand and learn what the height values should be, what's normal for a height of a particular component. Doesn't matter what the shape, and it doesn't even have to be the same height throughout. It can be some complex shape. And using that in the principal component analysis models to determine using the height information is another enabling factor to get you better inspection moving forward. And so, in conclusion, there's a number of different inspection challenges. I've talked about a few. There's also the implementation of the inspection that, to meet your needs. There's data, there's ease of use, there's different data outputs, there's integration into shop floor control. But inherently, the technology that is driving the data collection and measurement input determines how well your inspection can be. And finding a solution that covers most of the more difficult problems that are applicable for inspection technologies is what's important. So be aware of the different challenges and make sure that whatever inspection vendor you choose for 3D inspection can meet those challenges. That's all I have. Thank you.